Okay, let's hit the ground running here. Alright, so with covalent bonding, remember covalent is the shared relationship. Okay? It's I share one with you, you share one with me, we create a bond by overlapping the orbitals. Right? So the rings literally overlap, and the shared belongs to both. Okay, it's not, they're all mine, they're not all yours. We do talk about how the sharing is not always equal, but it's still being shared between them. Okay, so there's 3 different types of scenarios when it comes to sharing that we'll see. We have what is known as a single bond, which is this one up here, where it's just I share one with you, you share one with me. Those 2 electrons are in the bond, which is what these 2 dots between represent. And so they are now shared between us. Okay, now I show you this model of only dots just so you're familiar with it. But at this level of chemistry, we typically draw bonds as actual lines to show, but the line represents 2 dots, okay? So this is a single bond. Sometimes they'll do a double bond, meaning sharing 2 with each other. So in a sense, each line represents 2 electrons, okay? Now keep in mind when you're counting octets, because that's the goal of why they bond, the line counts for oxygen, so 2, 4, 6, 8. But they also count for the carbon. That's the idea of the overlap, right? So 2, 4, 6, 8. Okay? The goal is to get that full octet, to get that stability. That's why things bond. Okay? We also can have a triple bond, where it actually shares 3 on both sides, and so there's 6 electrons being shared. Actually, just a year or so ago, they actually discovered a very rare situation where quadruple bonds exist. But before that time, we didn't think they were possible. So don't draw them on your answers ever, because it's like extremely rare. So don't ever assume that a quadruple bond is going to happen. But they found a way, which it kind of does, which is cool. So, and then as we learned last time, we talked about these graphs. Remember that one? Right? And so the length of the bond, right, was directly related to how many times it was bonded. So, okay? All right. I'm going to throw up the rules just for you to kind of fill them in, because then we're really just going to kind of walk through practice problems. So I'll give you a minute here. Oh, I lost my mouse. There you are. Okay, so fill in these blanks for our rules that you can use as reference. Now, for those of you that took chemistry last year, at least at Skyridge, because I can't verify for other schools of what you learned there, but at least here at Skyridge, if you've taken chemistry before, I will tell you that the approach we're going to take in here may feel a little different if you weren't my student, which I don't think any of you were. Yeah, because I didn't have any of you last year. And the reason being is because there's certain things in general chemistry, certain exceptions that they just kind of ignore and don't teach. But in AP, we have to understand all the exceptions and all the possibilities. So I apologize if you're like, this feels weird, but hopefully you'll like it, because to me it's actually, it makes the exceptions very easy, even though they're exceptions, okay? The biggest thing to focus on as you're filling in these blanks is it's about valence electrons, right? Valence electrons are the only one that bond, and so you have to start with what you have, and you can't just add extra or take things away. You gotta work with what is given, and then figure out, okay, what are they gonna do to make each other, as we will say, happy, right? Bond to make their octets, okay? All right, everybody good? All right, let's do our first example. Okay, so the first thing we're going to do is build what I call the skeleton structure. So the formula that's given is PCl3. Okay, when there's one atom combined with multiple atoms, the one atom is the one that goes in the middle. Okay, so we're going to put phosphorus here in the middle. I'm going to surround it by 3 chlorines, leaving space in between them, once again, to build the bonds. Now the placement of them really doesn't matter. If you choose to put the Cl on top, that's fine. Like, doesn't matter. Okay? All right, now we got to start with what's given. So how many valence electrons does chlorine come with? Oh, close. It wants 1, so it has 7. There we go. So draw 7 dots around your chlorine. Now with the dot placement, once again, it doesn't really matter. We typically, once again, keep them in pairs, because that's how orbitals exist. And you typically kind of keep them top, bottom, left, and right. I highly recommend, which I'm seeing most of, the use of a pencil when you do these, because a lot of it will be, it might look a little messy when you first finish, And so then you kind of use a pencil to like clean up your image, right, to make it look nice. Especially if it was like an FRQ. Okay, add 7 to the rest. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. Phosphorus comes with how many valence? 5. So 1, 2, 3, 4, 5. So once again, draw your skeleton. Start with what's given. Then focus on the outside atoms. The inner one is just mostly going to take care of itself. So focus on completing the outside atoms octet. So it has 7, so how many more does it need?
1.
Just 1, so we're going to connect to create a single bond because that gives it 1 more. Okay? That gives it, once again, I'm going to draw circles just for counting purposes, but the circle is not part of your normal Lewis structure. Okay? But if I was to count the valence electrons here, right? 2, 4, 6, 8. Happy guy. Okay? Alright, this one, same thing. Let's bond it 1 time. I always do a check, right? 2, 4, 6, 8. Happy guy. Same thing here. Oh, wrong color. 2, 4, 6, 8. Also good. So make all the outside ones and atoms happy. Then you can check the middle and see what's going on there. So phosphorus has 2, 4, 6, 8 as well. And so we must be right because there's nothing else to do to make everyone happy. So you're done. Okay? Now once again, sometimes maybe in the end, like if your dots were like, you might want to move them around to like make it look clean, and I'll kind of show that as we go. But questions so far? FYI, for every smiley face you see today, you can have it.
Oh, come on. Me and Alex totally deciphered that.
Oh, I gave it away. But we're just excited. That's it. Okay. Next one. Ready? End of term. We gotta like fill those sheets up, right? Okay, so now we have the formula HCN. So now in this case, there's not an obvious center atom. So the way you determine what's in the center, Bryson?
It says the least electronegative atom besides hydrogen.
Good. So in your rules, first off, hydrogen never will go in the middle. Because how many times does hydrogen want to bond? Just once. Right? So it's never going to be in the middle because it doesn't want to bond more than once. So then between carbon and nitrogen, you compare which one has the lower electronegativity, which means to the left. And that's what will go in the middle. So carbon is in the center with nitrogen on one side, hydrogen on the other. Once again, if you chose to put N and H opposite, it's fine. Okay, start with what they have. How many does hydrogen come with? 1. Carbon comes with? 4. Nitrogen comes with? 5. You're probably going to unknowingly memorize valence electrons during this because you'll just look them up so many times. Okay? Alright, start with the outside atoms. So hydrogen only needs to bond 1 more time because its valence shell is only too big. Right, so that's happy. He's good. How many more times does nitrogen need to bond to get its octet? 3. Because it came with 5 and it wants to get to 8. So we're going to bond 1, 2, 3. Okay. Now nitrogen has 2, 4, 6, 8. He's happy. Check your center. 2, 4, 6, 8. Must be it. Now, if this was an FRQ answer, I would probably redraw my image really quickly, like that, because it just looks a little neater and easier to read than the lines kind of going all this over. But yeah, Levi.
So with like, will you ever have to rearrange it, like put nitrogen in the middle, or is it always in the order that it's supposed to be?
Good question. Nope. So there's no molecule that exists where it's H and C. It's not even possible. Yeah, good question though. Other questions on this one? Yeah, Garrett.
Should you always put it in order of electronegativity?
Yes. Yeah, so always by electronegativity, throwing hydrogen out of the mix. So even the ones where there's only one center, it's still gonna follow that pattern actually. So other questions before we try the next one? Okay, let's try another one that brings in another concept here. So this brought in the idea of having multiple bonds. Okay, this one brings in the idea of a charge. Now I noticed on your notes the charge is kind of a little ways away. So maybe emphasize, mine not small, it's not supposed to be small. You're supposed to have a -1 charge. Does everyone see that on your picture? Okay, so kind of emphasize that. It's so hard to type formulas. Google Doc does not understand chemistry. Like, it doesn't have a nice way to write formulas. Okay, so same thing as before with just some added changes. So we're going to put Br in the middle. I have 3 oxygens. Okay. Start with what is given. So how many does oxygen come with? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
Do we have to spread out the electrons like on all 4 sides?
It doesn't really matter, as long as in the end you have the right number of dots and the right number of lines. So, how many does bromine come with?
7.
7. So 1, 2, 3, 4, 5, 6, 7. And once again, that's kind of where in the end, Bryson, like I'd maybe clean it up if my dots in the end looked a little like not in pairs. So. Okay, now first thing to consider is the charge. This is telling us that this molecule as a whole has a -1 charge. What does that mean about electrons? There's an extra electron. It took it from somebody, sodium, who knows, but it took it from someone and the molecule has it as a whole. So we need to draw that electron in our picture. So when you have a negative charge, that means you're adding electrons, and you always add to something on the outside. Doesn't matter which one, but don't add it to the center. Okay, so you add 1 electron or more, depending on what the charge is, to outside atoms. Now, if we had more than one, distribute the love. Don't give all the electrons just to one of them, because then it may not want to bond in the first place. Okay, so in my case, I'm going to pick the top one. Okay, so I'm just going to add a bonus. I'm going to do it in blue just so, I don't know, just to know where it came from. But you normally just do it in your pencil, so it doesn't matter. Okay, if it was a positive charge, what does that mean about the electrons?
Less.
Yeah, so now electrons have been taken away and you do the opposite. So you take from the center atom. So when you have to remove electrons from the center. If you do the opposite, your structure is going to get really weird. Okay, so you remove from the center, but add to the outside. Okay, now let's go back to just the rules we did before. So how many more times does this oxygen need to bond?
2.
2, right? It has 6, it needs 2 more. 1, 2. I'm going to move this dot just to make a pair. Happy camper. Okay, the one on the top, how many more times does it need to bond? Just once, because it got the bonus, right? So it has 7. So I'm going to bond it once. Don't need to bond anymore. Okay, this oxygen, how many more does it need?
2.
Needs 2 more. So we go 1, 2. Okay, now once again, I'm going to just move some dots to make pairs. So I'm going to take this dot, put it there. I'm going to take this dot, put it here. Just makes it easier to see the dots and the lines when you pair them up. Okay, so all of our outside oxygens have their octet, right? What's going on in the center?
There's 12.
You have a lot, right? 2, 4, 6, 8, 10, 12. But guess what? He's still happy.
Oh, okay.
So this is one of those things that was not covered in general chemistry before. So if you haven't, it's actually to your benefit because now you won't know any different. But some atoms can do what is known as a hypervalent molecule.
God.
meaning 8 really isn't what it's about. We'll kind of talk about it later in lesson of why. Just pretty much know if you do the outside wet atoms and they're happy and it happened to overfill the middle, as long as it isn't, there's like 3 elements that cannot overfill ever. As long as it's not one of those, then it's good. And it's just extra happy, right? Extra electrons. Now there is one small detail you add when there's a charge. You put brackets around the molecule to show that it's charged. Right, kind of justifying where that extra electron is. Okay, any questions right now?
That was fancy.
Okay, now I apologize, so find where you want. There's supposed to be space for 2 practice problems and it's not there. So squeeze them in somewhere. If you want, the very back page of your notes is completely blank. If you want to go to the very end of the unit or just squeeze them in somewhere, I'm going to give you 2 practice problems for 2 more smiley faces to try with your table leg, okay? I want you to draw for me, do CO3 2- and SIF4. Okay?
Okay.
So try those 2 out with your table buddy, and then we'll check on for some smileys. Ephraim, did you raise your hand?
Yeah, I'm just wondering if you could
The problem is, so there's actually scientific ways to what a molecule looks like. And scientists have found that it actually has several bonds. So even though that like makes it seem like it satisfies
Six.
Okay.
6?
Yeah.
Does that make sense? So good question. And why don't you kind of on the next section with formal charges, that will kind of go into it as well.
And C has 4.
And C has 4.
Oh, it's 2.
And then 2 negative means you add 2, so right. And then you just add 2.
Wait, do we add 2 to this one?
You add 2 to, why do you add 2 to the beginning of it? So this one needs 1, I have some bonds. This one needs 2, so this one so then,
No, triangular bonds don't really happen.
wait, when there's
Good thought though.
when there's multiple O's, like you write it out, like how you did on the last. Like, okay, you did it on.
There you go.
You did it on. Like, how do you write it like this? Like with all that.
Oh, so pretty much it would just be like pairing up any lone dots so they're together. Does that make sense? So just be like erasing that one, erasing that one. So really, to like clean it up, all I look for are pairing up dots, and then if my lines happen to be kind of like crazy, then I maybe just like erase that dot, put it on the side so it like looks nicer. But once again, like if it was a multiple choice question, you just have to like pick it. It doesn't matter if it's messy. It's just when you clean it up, it's just easier for someone else to look at. So.
Alex, this is not me, so Alex is gonna pull up.
Are you helping a friend out? You were threatening.
You're threatening.
Threatening yourself?
Yeah. I just like hear it. I know what they do.
Like when I'm actually like writing a lot.
That's it. Yep, one double bond and 2 single bonds.
Hold on, let me get your water.
Is it the same?
We gotta keep
Yeah.
hydrated.
Is your brain supposed to work without water?
So SI goes in the middle, and then so S.
Well, water can only have.
There you go, Jack. Stay hydrated. Exactly. You got water. So you want to, let me get you some water.
I'd say level
You guys-
regular was that.
SAS 4.
Stay hydrated.
Yeah.
Because you need water.
This one's off.
Stay hydrated.
Well, I'm behind you.
I forgot what
You were drinking for like 5 seconds.
He's like actors, right? Where they don't like
I
really
do
drink
this
for
one.
the Okay, I'm walking around. I feel everyone's done with the practice problem. Anyone need any more time with the practice problem before we check them? Okay, I think we're good too. I'll write the answers up here just to make sure, but as I walked around, I didn't see anything that I saw wrong got fixed. So for this one, you should have had, so carbon's in the middle, you should have a double bond on one side, single bond on the other. Now remember that this one also should have brackets because of the charge. So that's what you should have. Questions on that one? Yeah, exactly.
We count the carbon with the double bond with the smiley face. You rotate it to the left, little.
Yes, yes you
That is
can.
smart.
Wow.
Drop your smile.
That's pretty smart.
Alright, and then this one should look like this. This one feels like a perfect match because it wanted 4, found 4 things to bond with, single bond on the sides. Questions so far with our rules of Lewis structures? Okay, now what we're going to talk about are some additional things to consider and then some exceptions that can happen. Okay?
Always accept.
So the first thing to consider is this thing known as a formal charge. A formal charge is a systematic way to identify whether a structure is correct. So the way they love to ask this on the AP exam is they'll give you multiple structures and they'll say, using formal charge, justify which one is the correct one. Now, if it's multiple choice, sometimes you really don't even have to do formal charge because using just the rules of Lewis structure, you can know which one is the accurate one. But if it's an FRQ, or sometimes on the multiple choice, they'll say, what is the value of it? So that's how we're going to learn it, okay? The formal charge equation is calculated by individual atoms. So you don't have to draw this because they're already on your paper. But for example, if it was given of carbon dioxide, could be drawn like this. Or carbon dioxide, what side did they put the triple bond on? The far side, thank you. Okay, and they're saying both of these satisfy octets, right? Like you count them up, they all have 8. But which one is the true structure of how it actually exists, okay? And Ephraim, this kind of goes along with that question you asked me of like, if you did formal charges for the structure, that's where you could kind of prove the difference. So, what formal charge is, now this, it's not my fault, but it's not on your formula sheet. There's a few equations that aren't there, and this is one of them. But it is somewhat straightforward. This is actually my interpretation of the equation because it makes it even easier to remember. So you're going to calculate how many valence electrons it has, which we already have to do for the shell. So take into account how many valence electrons. Okay, so for oxygen, how many valence electrons does it come with? 6. Okay, so now notice I'm only focused on oxygen, okay? Formal charge is individual. We're going to have 3 formal charges for the whole thing. So this oxygen has 6, okay? You're going to subtract the lines, or AKA the bonds. many bonds is on that oxygen in that model? 2. So 6 minus 2. Okay, then we're going to minus the dots, which are the non-bonded electrons. So how many dots are around this oxygen? 4. So 6 minus 2 minus 4 gives me 0. Which 0 is a good place for formal charge. It means it's stable in that arrangement. Okay, so let's calculate it for carbon now. So how many valence does carbon have?
4.
4 minus 4 lines, 0 dots, so also a 0. Okay, so this one's at 0, this one's at 0, and then if you notice, this one's the exact same as the other oxygen, so it's also going to be 0. So right there, that actually tells me that this is the valid structure, because they all have formal charges of 0, they're all in a stable arrangement. Just to compare, if I calculate formal charge of this oxygen, how many valence does it have?
7.
So you start with what it has, so it comes with 6,
Minus 1.
but then we're going to minus 1 minus
6.
6, and so now it has a formal charge of negative 1. Yeah,
But,
Alex.
okay, so if that one did not have that bond there would be 7 electrons around it though?
So the valence electrons are like what it came with before it bonded, not like what's shown in the picture. So like oxygen always has 6 valence. But that is why, like, that's part of why this is quite wrong, is because in the picture it's showing it's starting at 7.
Okay,
Does that make sense?
I think so. Like, would it, like,
Just don't do it that way.
sure, like if it was like an ion or something, I guess, I don't know.
And that's where, once again, like, if you had to, like, if you don't have, if it doesn't say calculate the formal charge, a lot of times you can look at it and be like, it doesn't make sense, right? Like, this can't happen for oxygen because it only comes with 6 to begin with. Sometimes I don't love it, but sometimes on the AP test they say, like, what is the value of the formal charges to prove your point? So, but if you don't have to use the charges, a lot of times you can just go off bonding habits of knowing, like, it just can't do that. So,
Okay,
does that answer your question?
I think so, yeah.
Okay. Questions on how to calculate formal charge? Now, the goal is for it to be 0. Okay, so rule number 1, we want it to be as close to 0 as possible. Now, sometimes it's impossible for them all to be 0, particularly if it has a charge. If the molecule is charged, the formal charges are going to add up to the charge. So in that case, the rule is that you want the negative charge, if it has to have one, to reside on the more electronegative atom. Okay? All right, so with your table buddy, I'll give you 3 minutes. Tell me A, B, or C of these 3 structures, which one is the dominant one, meaning which one is the most stable arrangement. Okay, ready, set, go.
So S. 6. S has 6 originally. 6 minus 1 minus 6. So negative 1. Times 4.
Yeah. It's 5 minus 2 lines minus 2
Oh wait,
And N is
minus 2 lines.
5.
oh wait, no.
Zeros, negative 1, 0. So S has 6, so 6 minus 2. Wait, minus 4? Yeah. Oh yeah, that's 4 dots. 0.
You'll see in other cases we like have to look at diagonals, but if you don't have to, I don't know what to choose to. But it's not wrong.
That's negative 1.
You should have, once you get to the conclusion, you should have circled A, B, or C. Which one is the dominant?
So, and this is
Oh wait,
6 minus and then
It's my building, so.
Yeah, the only thing is
You
they're
have
adding
one more minute to come to an answer.
So they said they added the electron.
No, in which one it's not.
Because when it's negative, you're adding silicon is more electronegative.
Wait, does it? Further down?
It could be C because when it's negative, you're adding an electron and being like multiplied by each other. That's positive.
Look at this, so with the rules, so they want to be as close to 0. So
But I don't
definitely
understand
throw
when
out
you're
C.
adding. I don't know when you're adding that.
So you're actually not, they've already in a sense done it for you, they came up with a structure.
Yeah.
You're just picking which one.
Yeah, but I don't know like when you add one, which one's more stable because they're.
Oh, so now the negative charge wants to reside on the one that's more electronegative. So is sulfur or nitrogen more electronegative?
So it'd be A.
The negative is on. Does that make sense? Where this one has a negative on sulfur.
So you did all of them. Just going through this. Just figure it out. Seven.
Thank you. Okay, ready? Show me. Hold your hand under your chin. Make an A if you think it's A. Make a B if you think it's B. Make a C if you think it's C. B or C. The correct answer, if you said B, have a smile.
We won the 50-50.
Okay. So once again, the two rules are you want them to be as close to 0 as possible. So C gets thrown out because this one has like +2, -1. Okay, so they're both far, they're not at 0, but these ones have 0, 0, -1, or -1, 0, 0. So then when they're equal in terms of there's only one thing that's not 0, that's rule number 2 of electronegativity should reside on, the negative charge should reside on the one with the higher electronegativity. And nitrogen has more electronegativity than sulfur does. Okay? Questions on this idea of using formal charge? Once again, it's not something you always have to do, but you may see a question pop up about it. Now, here's Ms. Alviso's shortcut. If you're running short on time on the test, and it's multiple choice, and you're having to, in a sense, calculate formal charge, I almost wouldn't, because if you only have like 10 seconds left, go with the most symmetrical one. normally it's the correct answer. This one has double bonds on both sides. Molecules tend to be symmetrical. Not always, but like if they can. So it's kind of a quick, once again, if you're running short on time and you just don't have time to calculate, that'd be my best guess if you go with the symmetrical. So, okay. Good so far on that? Okay, second thing to take into account with Lewis structures is when you can have multiple versions of the same one, but the formal charge doesn't change. Because it's really just a placement of the double bond. Okay? Now I changed this example because I just thought it was better. So on yours it said we're going to use the NO3 ion. Change it to O3, we're going to do ozone. Okay, so notice on yours it says consider, NO3. Oh my dear, go back. Okay, we're going to do O3 as our example. Okay, so the idea here is this, that if I draw ozone, okay, and we'll get into how this is drawn later because it's also kind of a weird exception on its own. But ozone looks like this in the end. So draw that image there. Okay. They all have an octet, all bonded 8. But if I put a mirror right here, what would the mirror image look like?
Right out of the way.
Yeah, double bond.
I don't know.
I know what you're saying, Bryson. The double bond is now over here. Which sometimes in picture it's like, oh, it's the same thing. You just do it in a different spot.
But it makes more sense.
But it actually is a different molecule when it comes down to what it is. Because this, let's call this oxygen A, and this is oxygen B. If you move the double bond, then it's a different atom that it's bonded to, even though they're both oxygen. Okay? Scientists found something very interesting with molecules like this. Okay? They have a way in which they can actually measure the length of a bond. Okay? So I'm going to show you the data of what they found, and let's see if we can figure out why it was interesting. Okay? So they know that a normal oxygen to oxygen double bond, so anytime there's an oxygen bonded to oxygen, the length of the bond is 121 picometers. Okay, picometers is just very small measurement. Okay? The single bond is 148 picometers. But what they found when they measured ozone is they didn't find either of those numbers. They found that both bonds were the same length and it was 128. So what is going on there? It's shorter than a double, but longer than a single.
1.5.
Kind of. So what happens here is when a molecule can exist, in a sense, in two different arrangements, but it's just a matter of where's a double bond, the conclusion is that the electrons get moved in our past. And so rather than being unequal, it becomes symmetrical. Now it's not really a 1.5 bond because it's constantly moving, but because it's constantly moving, it's giving that feel of a 1.5 bond. This is what we mean by we say that a molecule resonates. It goes from this structure to this structure, but so fast, like a flip book, that it looks like a perfect blend of both.
So it sort of follows like a metallic bond?
In the sense of like a movement of electrons, yeah, you could relate it that way. Yeah.
How do you write that then?
So that's the catch, is like, okay, well, how do I draw that as like a 2D picture? So the correct way to draw is you actually draw both orientations, and you put what is known as the resonance arrow in between them. Okay, so you do this double-headed arrow between the two structures. Now, sometimes that means like your answer can take up a lot of space because you have to draw like, sometimes they resonate in 3 ways. And so like you have to draw 3 separate structures. So to simplify your life on your homework, you don't have to draw all the structures. You can just draw the resonance arrow underneath your image and then tell me how many structures you would have drawn. Alright, so draw 2 for ozone, saying, oh, it would have resonated 2 ways. If it resonates 3 times, do a 3, but that way you don't have to try to fit 3 images in those little boxes. Questions on what resonance is or how I identify it? Yeah.
How do you know if it's 3?
So, an example would be, so like the one I did, this one. So that's a 3-way resonance, because it'll, once again, if we say this is A, B, and C, the double bond could be on B or it could be on C. Does that help? Yeah. Yeah, good question. Jack?
So basically how it works is like you have a bond that you can switch with another atom, then it's
Very well said, yeah. So what Jack said, how somebody used that, he said, really to identify resonance is you're looking for a double bond that can exist in different places and it doesn't like change the structure, right? Just think of mirror images. But because these are literally different elements, even though they're all oxygen, we have to recognize the difference of them. So yeah. Yeah, Ali.
So does that mean that it's still like a covalent bond, even though it acts like a metallic one?
Yeah, it's still covalent, in the sense of, because they're still being shared. It's not completely free range like a metallic bond like the ocean. But you actually bring up a cool thing. The cool thing is that something that's resonate actually can conduct electricity as solids. Yeah. So have you ever heard of carbon nanotubes before? They're really cool. But like, they are carbons that can resonate and they actually conduct electricity very well. So yeah, so it actually can bring in some cool metallic-like properties. So yeah, great.
I think you already explained this, but with the oxygen that has the 6 valence electrons,
Yeah.
the bonds, I guess it's just like how, why? Because then they 7 electrons.
Hold that, because ozone's a weird one. Are you saying because like this one is that idea of the 7?
It has the 6, but then it has the
Yeah.
extra
So
electron.
ozone's weird in a few ways. One is the resonating wave, but then the other way is how it's actually made. So stay tuned. We'll draw it again, and I'll walk you through how we get there. Because it's weird, yeah. Okay, questions on resonance? Oh, there we go. We saw that image. So this is just a picture of, just to give you an idea of other types as molecules get bigger, how they can bond, and then also how resonance happens. So resonance is often talked about in an idea of a pushing electron idea way. That if these bonds get pushed over here, those get pushed there, and then those get pushed there, and so then that's in a sense how you get those 2 different images. In the end, the electrons are just kind of going everywhere, which is pretty cool. So, okay, now let's go through our exceptions. Some of them we've already addressed, like the hypervalent, and then we'll talk about some of the other exceptions to our rules. Okay, so sometimes you have an odd number of electrons and it just doesn't work out. Okay, where it's just no matter what you do, they can't get an octet. There are special cases where it appears that way, but they still get an octet, and ozone is like that. But there will be like a disclaimer to let you know. So if there's no disclaimer, don't break the rules. So if I'm doing NO, nitrogen oxide, okay, and I'm just following the rules as we learn them, okay, how many electrons does nitrogen come with? 5. 1, 2, 3, 4, 5. How many does oxygen come with?
6.
6. 1, 2, 3, 4, 5, 6. Okay. Now technically there's only 2, but which one is considered the center and which one's the outside? Yeah, nitrogen would be considered the center, so let's focus on filling up oxygen first. So how many more does oxygen need? 2. Okay, so that's all it needs. We're not going to bond anymore. But if I check nitrogen, does it have 8? Nope. And it just doesn't. Just like that. These molecules, would you expect them to be stable or unstable? Yeah, they're very reactive. Odd-numbered molecules in biochemistry are often known as free radicals inside your body, which are not good because they'll go steal electrons from anything in there, which then can cause other things to happen which you don't want. So that's why you eat antioxidants to fight free radicals, if you've ever heard that before. But yeah, Bryant and Gavin and Jack.
So why do they bond in the first place if it's not gonna like
question, and a lot of the times is maybe it just is a little better than it was before, or the right situation made it happen. A lot of times they're kind of like a byproduct of a reaction, like this other thing, and then you have these random leftovers, and so they just found each other, but it wasn't really like what you were meaning to create in the first place. So yeah, definitely not something that's common, right? Like you don't commonly find them. So yeah, great comment, question. Have a smile for that.
So like, oh,
Why do you write them in 3 pairs on oxygen electrons and not like write them, because don't you
Oh,
space
like
them
the
out
other
to
side.
orbitals? Yeah.
Sorry, I kind of, once again, I knew where I was going, and I knew in the end it was only gonna bond twice, and so then I'd pair them up in the end. Kind of like with nitrogen, I probably would like take this one. So I kind of would just, sometimes the more you draw them, you can kind of see where it's going, and so I just paired them up. But if you would have had it like spread out, it's still yeah, good observation though, Gavin.
So that's like the final result.
Yeah, so that would be my final picture, where you just have that awkward, odd electron on your nitrogen. Levi, did you have a different question?
On the homework, it says both elements have to have a full octet.
So that's a disclaimer. So that's where it doesn't feel like the rules are working out, but we're gonna find a way to make it work. So I have an example of one of those we'll come to here, I think not the next one, but the next one. Okay, here's another example where it just doesn't get an octet, but you'll see this one even works out like, just kinda ends. So boron, how many does it come to the party with?
3.
3, so 1, 2, 3. Fluorine comes with 7. I don't know why I did that up high. Let's put my dot below. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, and so then give them all what they come with. Always focus on the outside atoms first. So how many more do they each need?
1.
Just one, so bond it one time. The fluorines are all good. They have 8. If you go to boron,
6.
and it's 6. But it, like, what else are you gonna do, right? Like, it only came to the party with 3 electrons to begin with. And boron will always do this because it only comes with 3. So, but just an example of where the octet is not completely followed. Okay, questions on that one? Okay, let's look at another example of a more than octet. So this idea of hypervalent molecules as we addressed. Okay? So phosphorus would go in the middle. Now when you have, this time we have 5 fluorines around it. So now we kind of break out of the left, right, top, and bottom, because you got to put 5. So I just kind of space them out around. Create a little, I don't know, star type idea. Okay? How many does phosphorus come with? 5. 1, 2, 3, 4, 5. Fluorines each come with 7. So you can kind of hopefully see where this is headed. Meaning phosphorus will bond once on each side. Oh, what the? There you go. There we go. And then they'll have their full outside shells like so. Now, with hypervalent, there's some things to consider. Number 1, it will only ever be the central atom. This little phrase is at the very bottom of your exception boxes, by the way. Okay? But it will only ever be the center. If you ever have an outside one that has more than 8, you've done something wrong. Just doesn't happen. Okay? The second thing is some elements are too small to go hypervalent, because it depends a lot on the D shell, being able to expand and use up the D level. But some atoms are too small and they don't have a D level because they're on period 2 or 1, meaning the row. So if it's on row 2 or row 1, they can never have more than an octet ever. Really the 3 to recall, because the others just don't really, or I guess the 4, okay, is that carbon, nitrogen, oxygen, and fluorine can never have more than 8. You give them more than 8, you've made up a molecule that doesn't exist.
Yippee.
Okay, so these cannot hypervalent. locking on more than 8. This is why even some of the noble gases bond with things. Is that even though they have 8, they just hypervalent and have more than 8. But the small ones never do. Okay, questions on that exception? Yeah, Alex.
So you're saying carbon, nitrogen, oxygen, fluorine can't, but boron and like all those other ones up there also would be able to, because they're not below.
I guess we could add boron to the list. Boron kind of like takes care of itself, like you can't even attempt to hypervalent it because you're going to run out of electrons. So you never really would run into a situation where it could. And then like covalently, metals don't covalently bond. So that's why I left off lithium and beryllium. And I guess we could add helium and neon to the list too.
Sure.
They're just kind of like, you're never even going to see them in a molecule. Like they won't ever be in a problem because they don't ever exist. But great clarification of others that people might not to. Person.
So does PF4 exist?
I don't think so because it's not really like, well, I mean, I guess no, I don't think so because you'd have to double. I don't know. I'll get back to you on that. I don't know if it exists.
Okay.
Try to visualize if it would be like
Well, I mean, you just
can draw
remove
it,
fluorine from the equation, correct?
and then you just have a lone pair. Yeah, it probably does.
And then you just, I mean, the fluorines would be happy, and then you'd have 8 valence for the phosphorus.
And then just one random electron. So you'd have 9 on phosphorus
Were you?
because phosphorus
okay.
comes with 5.
That's
Oh,
right.
yeah,
That's
that's true.
I would say it probably doesn't because that feels weird,
Okay.
but maybe.
Okay.
Okay, now Levi will address the one that you can have all the homework. So sometimes there are weird ways to get an octet. That's how I explain this exception. Now I'm going to be very honest with you. This is something I have been researching for the last 10 years. And I have not come up with a good answer yet of exactly why this happens. So I'm sorry I don't have a better explanation besides
triangle?
just saying it's weird.
Is it a triangle?
No, it's not a triangle, but weird things happen. Now, the way you know that you're going to do this is because there will be a disclaimer, right? Like on your homework, there's a disclaimer on some of the problems where it says both elements will have a full octet. Because what happens if you just try to follow the rules, it doesn't work out. So let's try this one here by just following the rules and seeing why you kind of get stuck. Okay, so oxygen to oxygen to oxygen, they all come with how many to the party?
6.
Okay, so give them all their 6. Okay, so following our general rules, who do I focus on first?
Awesome.
The outside one. So how many more does this oxygen need? 2. Go to the other oxygen. How many does it need? 2. Feels like things are going well. But what's the problem with the center?
I only have 6.
10.
Oh, no, it's 10.
And can it?
No.
Oxygen can't. So this does not happen. Because oxygen can't have more
Can't be hypo.
than 8. Okay, so let's restart. Okay, and say, all right, well, let's do the same thing as we did before. And say, okay, well, we'll double bond one side. But now let's just single bond the other. Okay. Well, why is that a problem? Yeah, they don't have their octets, and we are told that all 3 have an octet. So when you run into this problem of, okay, I can't hyper, and it often is the case of oxygen because you can't go bigger. Some weird things happen where the electrons get passed and shared in a not normal sharing kind of way. Okay? So in this case, this oxygen, do I need to change anything here? No. That one's good. What's wrong with this one? Has 2, 4, 6, 8, 9, right? Too many. How many? What's wrong with this one? So this one has not enough, right? 2, 4, 6, right? So the electrons get passed. Okay, so I'm just going to take this one away and give it I'm gonna move this one just to create a pair. Because now, does everyone have an octet?
Yes.
Did I add any that I didn't have to start with? Nope, I used everything I had, they just got pushed around in weird ways.
Are these kind of questions gonna be on the test?
So there was one last year, the CO one actually was on last year's FRQ. But they do specifically say, like, it completes the octet, so you kind of just move around what you've got to get it there.
So with the CO one, would you just make a triple bond?
Questions on this idea? Okay, all right, last type of thing, it's not really an exception, just another way, oh yeah, Ian.
So, it's on the homework, but like with the nitrogen and oxygen bonds, so can you put an oxygen atom to a nitrogen? Or is it only when they're the same atom?
Oh no, they could be passed to nitrogen, yep, so in those ones, yeah, the one that's like N2O,
Yeah.
yep, they can pass amongst each other. Yeah, good question. Any other questions on that? Okay, so the last one is just recognizing that you can have more than one central atom, but the rules still are the same. So just take it piece by piece. Now at this level of chemistry, they're going to give you the skeleton already. Okay, so the formula for this would have been just C2H2. Okay, so you don't have to like figure out how it's set up, you just have to add in the valence and connect the dots. So how many valence does hydrogen come with? One. And I apologize I spread these out too much. It printed and I realized it's kind of long lines. But how many does carbon come with? 1, 2, 3, 4. This carbon comes with 3, 4, 1. So once again, follow the rules like before. Just give them their valence. Then work from the outside and go in. So how many more does this hydrogen need? 1. So just connect. Come to the other outside. Connect. Okay, so now how many more does this carbon need? It has
3.
Okay, it only has 5 because 2, 3, 4, 5, so it needs 3 more. So 1, 2, 3. If I were to clean this up, it would just be HC bond. So once again, the rules are the same. You just kind of have to take it piece by piece when it has more than one central atom. Okay, that is it. Final questions. Yeah, Jeff. Once again, if they don't need to, they're not going to. So like, don't like force it. But if that's the only way it works to get the outside ones what it needs, they do. All right, we got 6 minutes. That's plenty of time to try a few problems on the homework. Okay, so pull out your homework. All right, let's use that time wisely.
Yeah, 1 and 7, so I move on to.
Okay, let me know if you got stuck, if I can help you.
These two are
Yes.
full. And I don't know how you bond them.
Start from the backtrack when like things have gone right.
They can't do this. Well, the ends are
Is it just, do we just have more, like, you can just,
The second one's CL or the L?
I mean, yeah, so it's chlorine. I know, that always looks good. Okay, so just like before, start with the outside ones.
Wait, isn't this an inside or does it not consider it?
It's considered an outside. It's the same as the inside element, but it's on the outside of the atom. Yeah.
something like this? If I do it right. I don't think
Okay,
it's
so
you
this one
outside
was
there.
good. So come back over here because we can't overfill the middle. So how many times theoretically could this one have bonded?
Oh wait, I see. So I bring this one over here.
Oh, I guess
Yeah, yeah.
okay. And then it always has like.
So it kind of just gets passed to.
I did it.
From the outside. Is that considered outside?
No, I haven't. Exactly.
If I had a bucket of magnesium, figure it out. Boom.
Oh, I might finish my
What
homework.
difference in a bucket means that this is like entire planet Earth, almost 50% of magnesium exists as ice bond.
That's
And
even
only about 10% exists as Does that make sense? So isotopes are not all created equal. So free isotope doesn't mean. That's what the percentage is.
Work on the other one. You got
Yep, how common, how naturally knowledge exists.
Edit.
I mean, I have.
So, this one, typically we start at the outside. So with one and every time we run into problems right away because, and so we know right from there, now we have this, we can only have one bond on each side of that. We'll also start with the bonds. One bond on this side, one bond on this side. You know what half the bond is? So now how that's drawn is oxygen have electricity.
Well, you don't have to put them over because they're already.
And then also, so we need to somehow give nitrogen more without taking away.
And then we add the ice bond to this one.
No, with the quadruple bond. Didn't we talk about this? Says definitely not allowed.
Not by
Double bond, so
erase.
So the one is on the non-radioactive.
Oxygen is donating and this is
Oh, it was H3.
Oh,
She explained it good. I understood it, but it's hard to explain. So like on this, if you do it normally, like so 6 But if you balance these two, both of those pills, so what you do is
FYI, there is an AP Chem quiz tonight too, just a short one about
yeah, you do it here. So then it's 1, 2, 3, 4, 5, 6, or last 7 and
of